Good evening, everyone. My name is Akhil. I'm currently a PhD student from IIT Madras. So, this is our week 9th session where we solve some of the problems related to the assignment from the course Machinery Fault Diagnosis and Signal Processing. To those who are viewing this today's session as first time, you can check out our YouTube playlist Machinery Fault Diagnosis and Signal Processing Jan to May 2023 live sessions, where you will find sessions we did for the rest of the weeks from week 1 to week 8. So let's begin the session. Yeah. So today's first question is regarding the vane pass frequency for a pump impeller having 20 vanes. Okay, so what would be the vane pass frequency at 600 rpm for a pump impeller having 20 vanes? So this is similar to something of this sort. A fan or something, you have this multiple n number. Now when you are doing the signal processing of these things, and this one is rotating at, let's say, some rpm, so here it's 600 rpm. So as each of these will give you there will be frequency corresponding to each of these units uh, going around. So as there are, let's say, 20 vanes, so 20 into rpm is one rotation of the entire thing. So in one rotation, because there are 20, there are actually 20 items crossing a certain point. So let's say this point, first this one crosses, then this one, then that one. So in a single rotation of it, there will be 20 crosses, or based on the number of number of vanes you have. So vane pass frequency would then be n into, we have for one rotation based on the number of vanes. So for 600 rotations, so and it's in rpm, so by 60 to get it in hertz. Okay, so it's basically number of vanes into rpm of pump by 60. Okay, so this is 20 into 600 by 60, 200 hertz. Okay, so the vane pass frequency you can estimate by just number of vanes into the rpm, and rpm is in minutes, so you need to convert that to seconds, so by 60. Okay, so this way you can estimate the vane pass frequency, which is called as Vp. Okay, now let's move on to the next question. Vane pass frequency and its harmonics are the dominant frequencies in the frequency spectrum for the case of increased turbulence. So when you are looking at the vibration characteristics of such a rotor, so of course you will have the vane pass frequency, and because of the turbulence you would actually see the harmonics also, and this will be dominant. So the answer is true. And one more thing is, when you have turbulence, this vibration signals, whatever you are seeing, will be modulated leading to in the case of severe defects, you will see this harmonics will actually look like side bands around ppf. Okay, so when you have increased turbulence or any other defects, you will have band pass frequency and its harmonics in the frequency spectrum. Okay, next question is in regarding rotary pumps. What are the possible origin for the different type of faults? In rotary pumps, the faults arise due to the presence of cavitation, unbalance, rubs, all of the above. So when you have rotary pumps, there is a phenomena called cavitation which happens specifically in rotary pumps due to uh, cause of high pressure and low pressure zones and formation of air bubbles which actually burst, and because we have rotating objects, if there is any unbalance or eccentricity, so it is also possible to have in a rotary machine, and rubs are also possible. So if any of the fans are touching the casing, if any of vanes are touching the casing, then it will happen. So any unbalanced mass, simply because any of the single, maybe a single fan is slightly heavier than rest of the fans, or one of the fans is slightly lighter than the rest of the fans, it is possible. Cavitation, formation of bubbles and bursting at very high frequencies. So all these are possible. So rotary pumps, you actually have all this. Cavitation is possible and balance is possible, rubs are possible. Um, the next question is again band pass frequency. So now the RPM is given as 1000, but it has 60 vanes. Okay. So as we discussed earlier, band pass frequency is number of vanes into RPM of the rotor by 60. So 60 into RPM is 1000 by 60, 1000 hertz. Okay. So this is the formula for the number of vanes. So this is same as the first question which you asked, but the numbers are different. Now let's look at the next question. In which of the following type of pumps fluid flow is continuous? either rotor dynamic or reciprocating. So there are mainly two categories of pump types. One is rotor dynamic and one is reciprocating. In rotor dynamic, the fluid flow is continuous, and in reciprocating, it is non-continuous. Okay. In reciprocating pumps, you will have the inlet and outlet. They open at different times. So you can actually create very high differential pressures between the inlet and outlet, and you will always send certain quantity of fluid at a time. So that is why these are called reciprocating or positive displacement pumps. Okay. Rotor dynamic will be a continuous fluid flow. So answer here is rotor dynamic. Which of the following is not a positive displacement type? So as I said in the last question, positive displacement type are kind of like reciprocating pumps where you have different inlet and outlet opening at different times and creating high pressure differentials. So gear pump is an example of that. Vane pump is an example. Reciprocating pump is an example. So of positive displacement pumps. Centrifugal pump is not a positive displacement pump. So to be sure, rotor dynamic pumps are the following. You have turbines, centrifugal pumps, axial flow pumps, fans, blowers, and rotary compressors. So these all are examples of rotor dynamic pumps. And when you come to positive displacement pumps, you have reciprocating pumps and compressors. So in pump you use water or sometimes of liquids, but in compressors you have gases, but they work on a similar principle, but the fluid type is different. You have vane pumps, you have gear pumps, and you have compressed air motors. Okay, so all these are examples of positive displacement pumps, and these are the examples of rotor dynamic pumps. So centrifugal pump is a rotor dynamic and not a positive displacement pump. Okay, let's move on to the next question. The internal walls of the inlet pipelines becomes fatigued and damaged due to looseness, misalignment, cavitation, or none. So we are talking about internal walls of the inlet pipelines. So we are talking about a type of pump become fatigued and damaged due to. So will looseness cause damage to internal walls of the pipelines? Misalignment? No. But cavitation does. As I told earlier, cavitation in certain cases, when high flow rates are delivered, so in outlet high flow rates in the outlet will need cause very low pressure at the inlet, so will cause low enough pressure at suction end, sometimes even lower than the atmospheric pressure. So this high flow rates in delivery will cause low pressures at suction, which sometimes could be lower than the atmospheric pressure, which then generates sporadic air bubbles, air or vapor bubbles. Okay, sporadic vapor bubbles, which actually move from low pressure to high pressure. So they are created at the inlet, which is actually low pressure, but these vapor bubbles actually move from low pressure zone to low pressure, where they are created to high pressure at the inlet side itself. And when this go to these high pressure regions, if the pressure becomes such a way that it could cause the bubbles to burst, so then the bursting of bubbles will happen, and this bursting can actually cause the damage to internal walls. And when this bursting happens, you will get a very high frequency vibrations. So this is also actually used as a method to see what kind of faults are there in the pumps. If you are getting a very high frequency vibrations, then it is mostly due to the cavitation. So once again, the internal walls of the inlet pipelines becomes fatigued and damaged in time due to the cavitation. And the reason why cavitation happens is because when you have very high flow rates in the delivery, the pressure at the suction end or the inlet end becomes so low that it sometimes could be lower than the atmospheric pressure itself. So that could generate sporadic vapor bubbles, which move from low pressure where they are generated to slightly higher pressure regions at the inlet side itself. But as they move to the high pressure regions, they can go to regions where they will start bursting, because they can be maintained only at very low pressure, but at high pressure they will just burst. They are not stable. Now as this burst, this bursting of these vapor bubbles actually damages the inlet walls, and you can characterize or see this bursting of bubbles as high frequency vibrations in the frequency spectrum. Okay, so this is why the inlet pipelines gets damaged. Next question. A gear of 30 teeth is rotating at 1200 rpm. Calculate the gear mesh frequency. So as we saw, similar to the vane pass frequency, gear mesh frequency is also similar. So gear mesh frequency GMF is number of teeth into rpm by 60. Okay, so teeth is 30, rpm is 1200 by 60. 600 hertz. Okay, so when you have multiple gears, or you have gear with a different number of teeth, and you have given the speed of the gear or the rotating speed of the gear, then you can calculate the gear mesh frequency. This is important because when you are observing the vibration characteristics of a gear or gearbox, you would actually find peaks at the gear mesh frequency. Okay. Next question. So what would be the reasons for failure in the gearbox? Lack of lubrication. Yes, it is possible. Presence of foreign particles. So when you have an oil to helping lubrication, and if there are any foreign particles, they might stuck in between gears and can actually cause faults. And if there are any manufacturing defects, that is the gear is not made properly or smoothly, or one of the tooths are missing, and if there is an excessive load that could actually damage the gears itself, will lead to the gearbox faults. So the question is all of the above. So the causes of gearbox faults: lack of lubrication, presence of foreign particles, or the manufacturing defects, or too much load. All of this could actually result in the faults of the gearbox. Okay, let's move to the next question. The vibration characteristics of a gear defect are the sidebands at. So if you don't have any faults, you are supposed to observe the peaks at only the gear mesh frequency. So your FFT would actually give you only the peaks at the gear mesh frequency. But when you have any kinds of faults in the pinion or in the gear, then you would observe side bands at based on the number of teeth in each of them. It could be happening due to pinion or it could be due to the gear itself. So this could be due to pinion and this could be due to the gear. Okay, this occurrence of these side bands indicates the gear defects. Okay, both are possible. Either it could be pinion or it's a gear. Okay, so answer is both. And because usually n is in rpm, you need to convert that to frequency. So that is why by 60. Okay. So these are the side bands and they will indicate that there is a fault in the gear. Now let's look at the next question. Fault detection using kurtosis comes under. So this we have discussed in our week 3, where kurtosis will actually tell you the shape of the graph. So let's see what exactly it is. Let's say you have this shape of the graph like a normal distribution. Then this is normal distribution will have a kurtosis of 3. Okay, and the way to estimate the kurtosis is from the data points which you have. X bar power 4 by number of data points minus 1 into sigma power 4, where sigma is the standard deviation, n is the number of points. Okay, so kurtosis indicates the shape of the certain graph, and if it is heavy tailed or heaviness of the tail, as you can say, as you can see, there are all the values are around this range, but there are very heavy tails, like very large values at the extremes. So this is a heavy tailed and this would have a kurtosis positive. Okay, now if you have a very low kurtosis or very low tailed, so this is low tail behavior, this would have a negative kurtosis. So based on the heaviness of a tail, you are able to detect a fault. So, and this is a characterizes a shape of a signal. Okay, so since it characterizes the shape of a signal as a function of time, so it will be a time domain fault detection technique. Okay, so when you are applying the shape characteristics, you look at the time domain itself, how the variation is. Okay, this question, for the case of a damaged gear, the vibration would be dominant in axial direction or the radial direction, both or none of these directions. So you have a damaged gear, which would be the dominant vibration directions. So the vibration will be dominant in actually both directions. So the answer is both, because when you have a damaged gear, it could be creating radial imbalances, creating radial forces, and the damaged gear could actually mean the load is not getting carried correctly, so it could actually also lead to axial vibrations. Okay, so it could lead to both axial and radial vibrations if it is a damaged gear. Okay, the ball, next question, the ball bearing works on the principle of hydrodynamic lubrication. True or false? The answer is false, because ball bearings are works on minimizing the friction using smooth balls. So they don't work on the hydrodynamic lubrication, but journal bearings work on the principle of hydrodynamic lubrication. Okay. Okay. I hope this is clear. We will move to the next question. What is the phenomena that happens in journal bearings when oil doesn't exert constant force on the shaft? So when oil doesn't exert constant force, then it's called oil whirling, and this happens because when you have a rotating system and some fluid, this is will be filled with fluid everywhere here. Now the outer surface is stationary, but the inner one is rotating at omega. So the fluid itself would also be rotating, and if it is not exerting constant force, then it would be tilted towards one side, and this would lead whirling of the oil. Okay, so when the journal bearings are not exerting constant force on the shaft, it will lead to oil whirl. And because of this, the actual rotating this, or the when you are looking at the characteristic frequency, you would see a frequency in the range of 0.42 to 48 times the RPM of the shaft. So you will get one more peak at this range due to the oil whirling. This is the characteristic frequency of oil whirl. So when you are looking at a frequency spectrum of a journal bearing, if you are seeing any frequency or any peak at this range of the RPM, that tells you that there is an oil whirl in the system, oil whirl defect. Okay. Now, the characteristic frequency of the oil whirl is usually less than half the speed of the rotational speed. As we saw, uh, because the whirl or the oil at the rotating unit will rotate at the speed of the shaft, and at the stationary side will be constant or zero rotations or zero velocity. So the oil would be actually rotating with a velocity in between these two, that is usually around 0.42 to 0.48 times the RPM. So it would usually be less than half the rotational speed, characteristic frequency. Okay, so it is true. Now, if this frequency, if by chance, if this frequency is close to the natural frequency, then it will lead to catastrophic falls, which is known as oil whip. Okay, only if it is this frequency of oil whirl, the characteristic frequency of oil whirl is in the range of the natural frequency, is close to the natural frequency, then resonance will happen and it will lead to even more falls or major falls, which is called oil whip. Okay. Sources of vibration and bearings are surface roughness, waviness, resonance, all, none. So if you have any bearings and if it is not smooth, let's say, so this non-smoothness when it is actually rotating will cause vibrations, right? So the surface roughness, or if it is wavy, that would actually lead to vibrations. So we have seen this, I think, last week also. Now, if the frequencies that generated due to this ball bearings are in the range of the natural frequency, then that will also lead to resonance, which would increase the vibrations even. So when you have in ball bearings, all the surface roughness, waviness and resonance, all of them will lead to the vibrations. Okay. Now because of these, the loads on the bearings will actually change because of the surface roughness, waviness and all, the loads keeping getting changed. So because of that, you would actually see an amplitude modulated wave, and that is due to the variations in load and speed because of the waviness or the surface roughness of the bearings. Okay. So the vibration signal from bearings is usually amplitude modulated due to variations in load and speed, and which happen due to surface roughness or waviness of the bearings. Okay. As you have joined just now, I am continuing, but I will revise everything once at the end of the question, all the questionnaire. Okay, now let's move to the next question. The high frequency of defective bearing is due to the excitation of resonant frequencies of defective races. So when you have these ball bearings, you have one inner disc, and in that there will be bearings, and there is one more outer. So this is the inner outer race, and this is the inner race, and these are the balls of the bearing. Okay. Now when you have very high frequencies are possible when there are defective bearings, and that is due to if there is any excitation, the frequencies are at resonant frequencies of these races. So if there is a fault in outer race, or if there is a fault in inner race, or if there is a fault in any of the balls, that would actually lead to vibrations. But if your frequency of the actuation, or if the frequency of the working is itself is such a way that you are at the natural frequency of any of these, then you would get very high frequencies uh, in the frequency spectrum. So it is actually true. Okay. And this high frequency of defective bearing is due to the excitation of resonant frequency of the defective races. Next question is regarding the engine firing frequency. So how many times basically you need to fire the or switch on the stage, or how many times the blast gets generated inside the engine. You have a 4-stroke 4-cylinder engine. So there is a direct formula for this. So RPM, so we are converting it to frequency, so RPM by 60 into, so number of times a shaft rotates into number of cylinders, because each cylinder there will be a single this thing, and by, or I will just write it this way, that's the formula, number of cylinders by K. K will be 1 if it is a 2-stroke engine, and K is 2 if it is a 4-stroke engine. Okay. So it basically means if you have a 2-stroke engine, then for every stroke you are actually doing the ignition. So, and each cylinder once, so it's just the number of rotations of the shaft into number of cylinders. So that would be the firing frequency. But when you have 4-stroke engine, you do at only once, not exactly once, you do only half of the times for each rotation, so you have to do by 2. So here it would be RPM is 1800 by 60 into number of cylinders is 4-cylinder engine by the type of stroke, it's a 4-stroke, so by 2. Okay, so it is 60 hertz. So the engine firing frequency is 60 hertz. Okay, so this is how you can calculate if this question is given: engine firing frequency, RPM into number of cylinders by K. I hope this is clear. Now next question. Again it's a question regarding engine firing frequency, but now you have a 2-stroke engine, but 6 cylinders are there, and the RPM is 1200. So what should be the engine firing frequency? I will give you a minute to calculate. So the engine firing frequency um, is RPM by 60. So here it's 1200 by 60 into, we have 6 cylinders by 2 strokes, so by 1 only. So plus 120 hertz. Okay, so this is how you can calculate the engine firing frequency if it's a 2-stroke engine. The next question: the loss of power in IC engines could be due to. So what could actually due to loss of power in IC engines when they are during the running operation? So in internal combustion engines, we actually have a gas that actually gets compressed, and a spark ignition which actually burns and expands the gas, which moves the rotor outside. So if the compression is not enough, then you would lose the power, and if you are actually firing, this sparking happens at a different instance than when it should actually happen, then that expansion of the gas won't happen. So again, this would also lead to loss of power. If your fuel quality is poor, it is not clear to able have that much carbon content, or such a way that that much expansion is not happening after ignition, so then also you will lose the power. So all of them would actually lead to loss of power in IC engines. Okay, so the compression, that is basically if you are not compressing the gas or the liquid strong enough, and if there is misfiring of the spark ignition, or if the fuel quality is very poor, then you would lose the power. . Next question. The vibration of the bearings are amplitude modulated or frequency modulated? So this is similar to the questions which you have seen earlier. So if the bearing is not smooth, or it has this surface waviness or some different things, then because of that the load at each instance keeps on changing, so it actually be leading to amplitude modulation. So this surface roughness could be due to scratches or fades or defects during manufacturing itself. It's all like surface roughness or the waviness. So this would actually affect the load. So they affect the amplitude of the system. So it's like amplitude modulated. Okay. So this is the last question for this week. I'll just revise everything now, and then we can close the session. So as you joined, I think today for the first time maybe. So my name is Akhil, and I conduct this weekly sessions every week, Saturday from 7 to 9 p.m. And today we are covering the ninth week sessions, and we'll meet again next week. And this week we looked at the different types of pumps, impellers, and bearings, and the gear mesh frequency, and so on. So the first question was, what would be the vane pass frequency at 600 rpm for a pump impeller having 20 vanes? So as it is rotating the rotor, for every rotation based on the number of vanes, let's if you look at one point, each vane will be passing once, but because there are n number of vanes in a single rotation, there will be n passes. So the vane pass frequency would be number of vanes into the rotations. So because it's an rpm, you need to convert that to seconds. So rpm by 60. Okay. So number of vanes into rpm by 60. So that gives you the vane pass frequency. So this is similar to the gear mesh frequency which we saw in the later questions. Next, if there is any defect or fault in this thing, so when you are actually looking at the frequency spectrum, you would actually see the peaks at vane pass frequency and its harmonics. Okay, so this vibration signals would be modulated, and in the case of severe defects, you would observe sidebands around VPF. These sidebands are basically at the harmonics. So the answer is true. They will be present in case of turbulence is also a kind of like a defect, as the fluid is not laminar, it would have uh, very chaotic kind of behavior. So this would actually lead to vane pass frequencies and its harmonics in the frequency spectrum. So yeah, in the next question we look at the rotary pumps and how what are the possibilities for the causes of faults. So one possibility is cavitation. Cavitation is the forming of air bubbles and they are bursting near the inlet or the inlet pipes, so that would actually lead to the faults. And when you are actually have this different vanes or impellers or the fans, if there is any unbalanced mass, then that would also lead to faults. And if any of the fans is actually touching the casing, like if any of them are slightly higher or lower such that they touch the casing, then this would lead to rub, so that would also lead to a failure. So the cavitation, unbalance and rubs, all of them could lead to faults in the rotary pumps. And again one more question on the vane pass frequency. So here the RPM is 1000 and there are 60 vanes. So number of vanes into RPM by 60. So 60 into 1000 by 60, vane pass frequency is 1000 Hz. Next we looked at rotor dynamic and reciprocating pumps or the positive displacement pumps. So in which following type of pumps the fluid flow is continuous. So only in rotor dynamic pumps the fluid flow is continuous. In reciprocating pumps it would be non-continuous, as you have inlet and outlet opening at different intervals, which actually will lead to high pressure differentials, and that's why they are called positive displacement pumps. So first, while you are inletting the fluid, outlet is closed, only the fluid comes in, and then the inlet is closed and then the outlet opens while you are pressuring the fluid. So you have a very high pressure differentials. And these are the reciprocating pumps or the positive displacement pumps. And the fluid flow here is continuous, as inlet and outlet open at different times. So once the fluid goes out of the inlet, again it gets closed and inlet opens. So when the outlet is closed, there is no fluid flow. Next, which of the following is not a positive displacement pump? So centrifugal is actually an example of rotary pump. So it is not the positive displacement pump, but the gear pump, vane pump and reciprocating pumps are all positive displacement pumps. Some other examples for each of them are, for rotodynamic pumps you have turbines, centrifugal pumps, axial flow pumps, fans, blowers, rotary compressors. All these are examples of rotordynamics. These three you might be dealing with fluids like water or petrol or any of these. For fans and blowers you might be dealing with gases. These are for mainly for liquids. These are mainly for gases. But all of these work on a rotary principle. In positive displacement pumps we have reciprocating pumps and compressors, vane pumps, gear pumps or compressed air motors. So all these are examples of positive displacement pumps. I hope this is clear till whatever we discussed till now. Also this notes and the video will be available even after the session. You can refer back if needed. Next, the internal walls of the inlet pipelines become fatigued and damaged due to. So the internal walls of the inlet actually get damaged due to the cavitation, which occurs due to some situations where you have very high flow rates in the delivery side, that is basically at the outlet, which in turn generates very low pressures at the suction side, okay, because of the high flow rates. Now if that pressures get so low that they are lower than the atmospheric pressure, then sometimes it is possible to form that it forms sporadic vapor bubbles, so random vapor bubbles, which actually move from low pressure to high pressure regions in the inlet itself. Okay. Now when they go to slightly higher pressures, Now again they are not unstable, so they burst out. Okay, when this bursting happens near the inlet walls, that will actually damage the internal walls of the pipes. So this is cavitation, this formation of sporadic vapor bubbles and their bursting. This is called cavitation. Now, if cavitation is actually happening, you would observe very high frequency vibrations in your frequency spectrum. Okay, so this is one way to identify if there is cavitation in your system. If you observe any high frequency vibrations. Okay. So in the next question we have the gear mesh frequency, which is calculated similar to the vein pass frequency. So you have the number of teeth into RPM by 60. So that would give you the gear mesh frequency. So here 30 teeth and RPM is 1200. So 30 into 1200 by 60. So it gives around 600 Hertz. Next question. The cause of gearbox defaults or faults in the gearbox. Lack of lubrication is one possibility if there is not necessary oil inside the gearbox for the smooth functioning. If there are any foreign particles, they could actually stuck in between the gears and cause problems. If there is any manufacturing defect or if there are any excessive loads. So all these are actually can cause gearbox faults. So all of the above. So when you are when you have any gear defects and you are looking at the vibration characteristics, you would observe side bands. So first, when you have a gear, you would observe a peak at the gear mesh frequency, and if there are any faults in pinion or the gear, you would observe corresponding the side bands. So side bands are basically a correct plus or minus. Here you are in RPM, so you are converting that to frequencies. So gear mesh frequency plus or minus the frequency of the pinion or the motor. So this would actually tell you that there are some defects in the gearbox or the gear. Okay. So one is gear and one is pinion. So both are possible. So the answer is both. Vibration characteristics of gear defect. You will say side bands. No. Yeah. Fault detection using kurtosis comes under. So kurtosis is actually one of the one of the quantities to characterize a shape. So it actually tells you how heavy or the tail is. So blue one is the normal distribution, so it will have a kurtosis of 3, and the red one is very heavy tailed. So there is a heavy tail and it will have a positive kurtosis, and the black is low tail and it will have a negative kurtosis, and it can be estimated this way. And since we are looking at the shape of a graph or shape of a signal, so it's actually a time domain fault detection technique. You are looking at the shape of the signal which you have obtained with the time and then saying if there is a fault or not. Next. For the case of a damaged gear, the vibration would be dominating. So when you have a damaged gear, both axial and radial vibrations both would actually possible. So the answer here is both. The ball bearing works on the principle of hydrodynamic lubrication. Journal bearings work on the principle of hydrodynamic lubrication, and ball bearings work on minimizing the friction using smooth ball. So it's false. What is the phenomena that happens in journal bearings when the oil doesn't exert constant force on the shaft? So when oil doesn't exert constant force, that is, it is one-sided. So that would actually leads to whirling. It's called oil whirling. So you have an inner one rotating at a higher speed and an outer stationary. Then the oil in between would be rotating at in between speed, mostly 0.42 to 0.48 times the RPM. And this characteristic frequency of this would be around this, and this is the phenomena of oil whirling. Now if you are actually very close to the natural frequency of the system, if these frequencies, then it would actually lead to catastrophic failures, which are termed as oil whip. Okay. Now the characteristic frequency of the oil whirl is usually less than half of the rotational speed. That is true, as we saw here, it is 0.42 to 0.48 times the RPM. Now, what are the sources for generating vibrations in bearing? Surface roughness, waviness, resonance. All of these are actually possible, and they kind of are the sources for vibrations in the bearing. So answer is all of them. So when you have surface roughness, the load keeps changing, so it could generate vibrations, or if you are any waviness in the bearing also. Next, the vibration signal from bearings is usually amplitude modulated due to, so that is mainly due to variations in load, and when you have the rotational speed also varying, then also you will get amplitude modulated. So the answer is both. Now, high frequency of defective bearing is due to the excitation of resonant frequency of defective races. So the races here correspond to the outer race and inner race of the bearings. So when they are at faults, and as these balls are actually rotating inside this, they would actually generate very high frequency vibrations. So because for a single rotation, based on the number of balls are present, so there will be that many times the passing of this over the fault, so you would actually get a very high frequency vibrations. Next we looked at the engine firing frequencies. So the engine firing frequency you can estimate simply as number of rotations per second, so that is RPM by 60 into number of cylinders by K. This is to check whether it's a two-stroke engine or a four-stroke engine. So if it's a two-stroke engine, you will be firing once for every rotation, but if it's a four-stroke engine, you will be firing every two rotations. So that's why by 2. Okay. So here it's a four-stroke engine, so you need to do divided by 2. So first RPM by 60 into number of cylinders by 2. That would give you the engine firing frequency. Next we have a engine firing frequency of a two-stroke 6-cylinder engine. and the RPM is 1200. So same. Now here K is 1 because two-stroke engine. So you get the engine firing frequency. Actually, in IC engines, it is possible to lose power due to which of the following reasons. So if there is weak compression, then the gas or the fluid or the fuel is not in a state to actually ignite, so there might not be ignition, so that could cause to loss of power. And if there is any electrical misfiring, so instead of happening at, let's say, first second, it happens at second or third seconds. When the fuel is not in the state where it can ignite, then that would lead to loss of power. Or if the fuel quality is very poor, then also it would lead to loss of power. Next, the vibrations of the bearings are usually amplitude modulated due to the variations in load, due to scratches or pits or defects like surface roughness and waviness, which would affect the load. So it's usually amplitude modulated. So that is it for this session. This will be uploaded in YouTube and the notes will be uploaded. Thank you.